Hello everybody, we're looking at our next lesson here. So we are on the second section, so this is title 2.8.2 and that's B. So it's the second section of rotational dynamics. So this one we're going to get more into depth on that Newton's second law and the moment of inertia. We'll talk about that, relate that to regular inertia and some calculations behind that. Okay, so begin by looking at our bell ringer here. So if a car does donuts with a radius of 6 meters and completes one full circle every 3 seconds, what's the car's tangential or linear velocity? So that's just a fancy way to say what's my linear velocity. What is the car's rotational or angular velocity, and explain the problem or process for solving each. Okay, so I have some equations here. This is linear velocity, so that is my radius, and that is my angular velocity. That's r omega, little omega. And then we have our angular velocity here is my change in radians, or my change in degrees over time. And remember, you do want to use radians for that. Okay, so you'll have to kind of do our conversion with pi to see what we get there. Okay, so let's kind of think about this. We got a car. Let's kind of draw a circle. Oops. Our car is doing donuts, so it's a car right there, and it's doing donuts. Radius is 6 meters. Okay, and then it says one full circle, so that's one revolution is going to be every 3 seconds. Okay, so we probably want to get this first. I know that's the second question, but let's see if we can get that. So we have our change in angle there over time. So we're going around one full circle every 3 seconds. So this would be, what would that be if we're doing one full circle? That's 2 pi every 3 seconds. Okay, and I would like you to put this in decimals. Don't leave it in terms of pi. So take your calculator, 2 times 3.14 or 2 pi. Divided by 3, and that's going to give me 2.09. So that is 2.09, and the units are radians per second. Okay, so that right there really goes with my angular velocity. That is omega angular velocity. Now we can come over here and do that one. So we're going to turn our angular velocity into a linear velocity. So that is 2.09. I got the order messed up a little bit here. Let's just go with it. So that's my angular velocity, and we have a radius of 6 meters. Okay, so you take 2.09 times 6, and we get 12.57. Okay, so that's 12.57, and that's going to be in meters per second. Okay, so we have our linear velocity here, which is just v, and over here we have our angular velocity of 2.09 radians per second. So not too bad. This stuff would be from lesson 1 if we're just kind of thinking of linear velocity quantities and angular velocity quantities. There also is angular acceleration, so that's change in our angular velocity over time. So those are a few equations that we have that we've covered. There are like 6 of them. Okay, so on to the lesson here. So I have a video here that just kind of talks about torque. This YouTube channel is Flippin' Physics. I'll upload that, or I'll put that in the post as well. So this guy does a really good job in his videos. So some of them are kind of corny. So if you want to watch it, review torque a little bit, go ahead. We're going to talk a little bit about torque here, just to kind of review what we did yesterday, or what we did in the last lesson. So this is just a pencil, right? So really basic pencil here. We have a penny taped on that end and a penny taped on that end. And we have this pencil here. So this would be our fulcrum right there. Or that's our axis of rotation, our point of rotation would be right there. Okay, So thinking about net torque in this situation, if we just have a single penny down here, and then we have our penny down here, we're going to assume that this is the same length as this part, and then we can say that that is a balanced system. Okay, so if you have a penny, which is usually 1 gram, okay, you would have to convert that. If we wanted to do the actual equation for torque, which if you remember, torque is, in this case, it's just going to be force times lever arm, but we could have that angle component, but this is straight down. So you have to convert the weight, or not the weight, the mass here, excuse me, into a force. So if I take that 1 gram, that would be 0.001 kilograms. We'd have to take that times 9.8. And then this would just move my decimal place over 3, so it'd be boom, boom, boom. And so that would be 0.0098 newtons. So that's the force from that penny, and that's the force from that penny. Okay, a little quick review on torque there. Oops. Okay, so remember, talking about this piece here, torque and equilibrium, we ended our last lesson talking about net torque. This penny will cause a rotation like that if I didn't have it balanced. And then vice versa, that penny would cause a rotation like that if I didn't have it balanced. But since these are balanced, it's not rotating at all. Right? So if I took one person off the seesaw, 1 penny off the pencil here, then it would just rotate in this direction. Okay, so that's a quick little review on torque for you. So we have a problem here with torque. So we have Carrie Ann, she's 56 kilograms, and Aisha, 43 kilograms. They want to balance on a 1.75 meter long seesaw. But now we're trying to figure out where we should put the fulcrum, or the point of rotation. Okay, so this is kind of backwards from what we did the other day. The other day we had it right in the middle, but now we kind of have it off to the side. We have to figure out where this is. Okay, so it's a little bit more complicated. First of all, we want to figure out, let's write our equation for torque again if we're trying to find a system here. We got torque of Carrie Ann, that's going to be equal to the torque of Aisha, or Aisha, however we want to say it. Okay, so for each of those we need a force. So force of Carrie Ann, force of Aisha. So Carrie Ann is 56 kilograms, and we're going to take that times 9.8 because that will give us our force due to gravity. And then Aisha is 43 kilograms. Take that times 9.8. Okay, and then the problem here, I'll get these numbers here in a minute, is we don't know where we want that fulcrum. We know that the seesaw is 1.75 meters long total. Okay, and we're assuming that that's massless. If we take into account the mass, then we have to use our moment of inertia stuff, which we haven't gotten to yet. Okay, but we do know that we're going to have some kind of a radius or a lever arm for the two of them. What can I say about that and that? Well, I know that those two together, if I add those together, so radius of Carrie Ann plus the radius of Aisha, that's going to be the total length of my seesaw. Okay, and that's beneficial because we're going to have to use that in our equation. So let's get these numbers here quick. So 56 times 9.8 and 43 times 9.8. So for Carrie Ann, I have 548.8. And that is measured in newtons. And Aisha, we got 421.4 newtons. So now let's use our equation for torque, which is going to be both of those, force times radius on the left, force times radius on the right. So we got Carrie Ann on the left. Let's plug stuff in. So we're going to have her force, 548.8 newtons. times her radius, okay, which we don't know. And then we're going to have Aisha's force on the right. And then we're going to have her radius. Okay, so now we have two unknowns in this equation here. I don't really know what we're going to have to do. Can we use this equation somehow to make those two unknowns turn into one unknown? Well, think about back in the day, if we have two equations, we're trying to find two unknowns, we have two equations. Well, we can take this equation and solve for one of the unknowns. That's called substitution. So let's solve for Aisha's radius, and I would have to move that to the other side, like so. Use a little bit of algebra, and I have this equation now, 1.75. That's meters. Unit doesn't really have to drag along with us right there. So now what can I do with this equation? I can take that, and I can plug it into there. So let's do that. So 548.8 RK equals 421.4 times that equation I'm plugging in right there. So 1.75, minus R sub K. Okay. Now, this is a pretty basic algebra problem. We distribute through there, and then we're going to have to solve for that variable. So let's do that. Okay, so 421.4 times 1.75. And I got, I'm going to show my work here, 548.8. Got to keep that RK over there. I have 737.45 minus 421.4 R sub K. So I'm going to move this over. Okay, and then we'll add it to this one. Oops. And we got it gone there. Let's write our next step below. All right, might run out of room here. I'll fix that. So 548.8 plus 421.4. On the left-hand side here, then I'll have 970.2. Oops, get rid of that eraser there. 970.2, and that we still have to maintain that variable there. That's that radius we're solving for, so don't forget about that. And then we have 737.45. And now we're just going to divide that over here. All right, I'm just going to do that in my calculator. So 737.45 divided by what I had, that 970.2, and I get 0.76. So 0.76, and that will be in meters, because that's actually the radius that we solved for right there. So Carrie Ann is going to be 0.76 meters away from our lever arm. Okay, so since we have that wonderful equation that we have right there, we can also find the radius of Aisha. Okay, so I would just do 1.75 minus that. So 1.75 minus my answer, and I get 0.99. So 0.99 meters. So that's how far away they are going to be from our lever arm. Okay, so the pivot point should be 0.76 meters here and 0.99 meters here. Okay, so this part right here was really the ticket to solving this problem. I had to understand that I have that radius plus that radius will equal my total length of the seesaw, which is that 1.75 meters. Okay, so let's check out another one here, or the second part to the problem. So suppose that Aisha is replaced by 52 kilogram Mario in the example problem. Where should Mario sit? So now we're going to figure out Mario's radius. So we have Carrie Ann there still. Let's say we have our rotation point there. She is 56, I think, if I remember right. She's 56. And we know that she is 0.76 meters away from that rotation point. Okay, now we got Mario. Well, he's 52, so he'll probably have to be a little bit further than that. So we can he's not going to be all the way out at the end. There's Mario, and he's 52 kilograms. Okay, give him a little Mario hat or something. We need to figure out this value right here. So radius for Mario. Okay, so this one is going to be just like the problems that we did in the last lesson. We're just going to calculate that lever arm right there. So we have a torque due to Carrie Ann, we have a torque due to Mario, but we don't know that radius. So let's find it. So let's say torque on the left, torque on the right. You could say Carrie Ann and Mario there if you wanted to. Carrie Ann's torque, and we actually figured that out above. Actually, we didn't because we had to plug that in. So her torque is going to be 56 kilograms. And I'm just going to write each step here times 9.8 meters per second. I have that number up above already. And her lever arm or radius is 0.76 meters. So this will take care of her torque on the left. Mario, we got to do kind of the same thing. So 52 kilograms. We have acceleration due to gravity to get that weight. And then we have his radius, which we don't know. So we're going to have to divide that out, 52 and 9.8 from both sides. And then we should be left with our radius there. I guess just kind of realized I did this. If we wanted to kind of save a little bit of calculator work, that 9.8 is going to cancel out. You can have it in there if you want to. We should all get the same answer. So I'll take 56 times 0.76, and I'm going to divide that by 52. And oops, so 42.56 divided by 52. I get 0.82. So Mario is going to be 0.82 meters from that point. So this right here, our radius there is 0.82. So like we said, it's going to be a little bit further away than Carrie Ann. Okay, so this one might be slightly confusing because you're like, well, maybe it's like the same before where I was moving this. I wasn't moving my point of rotation, my lever or my fulcrum there. I just wanted to put a different person on there and see how far from that point he should be. Okay, so we're not moving that because we had to figure out where that was in this problem. Okay, so these are a couple torque problems that are a little bit more complicated. Hopefully they make sense to you. So the next topic here, we kind of just hammered through some torque problems. The next topic is moment of inertia. And again, I have a video link with this. Slide that I'll share with everybody. So we kind of have to discuss what inertia is to understand what the moment of inertia is. Okay, so let's focus on this word right now. Inertia is a kind of a property of the object. It's its tendency to stay at rest or tendency to stay in motion. Okay, so this inertia is a property of an object. Okay, so now expanding that idea, talking about what's called the moment of inertia. So each object could have its moment, which is essentially that property of inertia. Okay, so this is kind of giving a fancier name to inertia. So each object is going to have its own ability to stay at rest or stay in motion. Okay, so what inertia does here is this: we're talking about the resistance to rotation, since we're talking about rotational systems here. So the moment of inertia would go with the resistance to rotation. Okay, so that is called the moment of inertia. It's represented by the symbol I. It's a capital I, and has the units of mass times the square of the distance. Okay, so we'll scroll down here. So for a point object located at a distance r from the axis of rotation, the moment of inertia is given by the following equation. So we have mass and radius squared. Okay, so a lot of the times mass, we're going to be using kilograms. We could also be using I think pounds or stones. Most of the time we're just using kilogram, and radius will be meters. So our moment of inertia is going to produce a unit that is kilogram meter squared. Okay, so it's kind of a goofy unit, but we have to have that mass and that radius. So if we're talking about this equation a little bit more, the radius of the mass is really going to affect an object's inertia. Okay, so if a mass is further from the point of rotation, then it's going to have a greater moment of inertia because it would have a greater radius. Talking about the flip side of that, if the radius were small, then it would have less of a moment of inertia. Its I, or its moment of inertia, would be smaller because we have a smaller radius. Okay, so let's check out an idea here. So you could do this at home, you could do this in class, whatever you want, kind of play around with this. So for an extended object such as your textbook, you can find a book somewhere. The moment of inertia depends on the distribution of the mass. So if we're talking about a book, or physics book here, the mass is going to be pretty evenly distributed throughout the book. This could be like if you had a hole in the book there, then the mass would not be as even, but we're going to be talking about objects that are fairly even. And then it depends on our axis of rotation. Okay, so if you took a physics book and you held it on the end like that, and then you tried to kind of rotate it back and forth like the picture is showing here. You rotate it back and forth. If you do that for a while, your wrist might kind of start to get tired because you feel like it's kind of hard to rotate it. If we take it and put our hands in the center of the book like that, and then we try again to rotate it, both ends here are going to be rotating. You might find that this one is quite a bit easier to rotate. Now, the explanation for that, you kind of think about it a little bit. So, distribution of mass plays into effect here, and axis of rotation here. So, talking about this example, I grab it down here on the bottom. Where is most of the mass going to be? Well, most of the mass is going to be along here, right? So I'm trying to spin or rotate that entire book from one end. Okay, so this is going to be a little bit harder. So that is going to be 1/3 mass times radius squared. Now these are kind of formulas. I would give you a formula that you would need. So for the second object here, or the second idea here, if I grab that from the center, okay, well, that's going to be a lot easier to rotate because I have a little bit of weight here and a little bit of weight here. I'm closer to the center of mass for the object, so that's what we're going to be talking about with our moments of inertia. So the center of mass, my hands would be right in the middle there. If I'm thinking of like a center of mass for the book here, let's say it's right in the middle, that's a lot further from where I'm spinning it, right? So my center of mass to my axis of rotation would be right there. Here, I'm right on the center of mass, so I'm rotating it about that center of mass. So that should make that easier. And if we look at the formula that goes with that, so this could be like a flat rectangular prism, I guess it might be what they call it, okay, or a rod of length L. But the equation for our textbook, which I would say it's a rectangular prism, would be 1/3 mr squared when we grab it here. Now if we grab it here, the equation goes to 1/12 ml squared, I guess. So that L is just the length of, so we're right kind of on the axis of rotation. But I would look at the fractions here. So 1/3 of that versus 1/12 of that. Which one's going to produce the smaller number? That one is, because 1/12 is a lot smaller than 1/3. So our moment of inertia here is going to be a lot smaller, which means since I is smaller, your moment of inertia is smaller, it's going to be easier to rotate. Okay, so this one it would have a smaller I, or moment. The moment will be smaller there. Okay. So this kind of talks about what I just talked about. So to calculate moment of inertia, you have to calculate total moment of inertia based on the axis of rotation. So this will lead us into our next problem here. So going back, so we could read that, you could pause that. This one, I am rotating this end from me. So really I just have one mass that's rotating away from my hands. So for this one, we would have to consider the mass on this side of the axis of rotation and the mass on that side of the axis of rotation, which is equal since I'm in the center. So that's what that L squared stands for. Okay, so we have the top of the book and the bottom of the book that are rotating, so we'd have to account for both of those masses. Okay, so hopefully, and that makes a little bit more sense. It's kind of a really easy, you get a book, help you understand moments of inertia, and the video would also be helpful to check out for understanding a moment of inertia. It's Walter Lewin. He's a retired physicist, and he uses a lot of these objects to show you which one, or he asks questions in the video, and the questions go along with this kind of stuff. It kind of helps you figure out which or what's moment of inertia is. Okay, so let's look at these. You would be given this chart if you needed it, or you would be given these formulas if you need them. So this is going to be like a hoop. Okay, so you might want to relate to these whenever you're working through the book problems, or you could copy this chart down or something like that. So this would be a hoop. This is going to be like a solid cylinder, our sphere, and a long uniform rod of length L. So this would just be like a metal rod or something like that. It's going to change a little bit. So this would be like if we had it in the middle of our book on the last one. Okay, and then it changes if we have it on the end. We're grabbing it by the end. And then this would be our rectangular plate or rectangular prism. So this would be more like our book. And we're spinning it around the center, which you should recognize the 1/12. Okay, so we can kind of generalize objects in the world that we work with. There's probably more than this, but these 6 things here, we can generalize quite a few things as these 6 things. So like if you were thinking fruits or something like that, most fruits, I guess, unless you're like a pineapple could be considered that. Apples, oranges, grapes, whatever could be considered that. I'm thinking food, I guess, but a lot of objects, baseballs, basketballs, whatever. This could be a hockey puck. A lot of things can follow these shapes, okay, or a combination of these shapes. Okay, so here are our equations, and notice which one is going to have the greatest moment of inertia. Okay, well that's 1/12. Oh, there's a 1/12, so they're probably close to the same. We got the different radius back there, because this one has to go with length and width. That one just goes with length. Alright, well that's 1/3, and we got 2/5 there, and we got a half there. So that one's going to be a big one. Well, this one here, there is no fraction in front of that one. So that's just going to be whatever the mass is times the radius squared. Well, that's goofy because, well, there's nothing in there. It's an open circle. It's a hoop. Well, remember, moment of inertia relies on the mass of the object and the radius from the axis of rotation. If we're talking about a hoop here, all of the mass is going to be on the outside of the hoop. There's nothing in there. So I compare this to a discus. So a discus has different rim weights that you can purchase. So you can buy like a 93% rim weight or a 95% rim weight, or you could buy an 80% rim weight. And that talks about the percentage of the weight of the discus that's on the outside. So if we were talking about a 95% rim weight, that means 95% of that is going to be on the outside. So a 95% discus is more likely to resist rotation. However, if you have a hoop, you guys have seen maybe the little toys or the frisbees or something like that. These fly really good if you can get them spinning. So that's kind of the idea behind a discus. A higher rim weight discus will fly better if you can overcome that inertia and you can get it to spin a lot faster. So it's a lot harder to spin it though because it has a greater moment of inertia. So a little bit of track and field stuff for you. So let's look at a problem involving moments of inertia. Okay, so we have, we have two batons there. Well, two different ideas with the baton. So simplified twirling baton with a round object at each end. The baton is 0.66 meters, so you can see here 0.33, 0.33. Mass of each object is 0.30. Find the moment of inertia of each baton as it's rotated about an axis. For the first one for the midpoint and the second one on the end. Okay, and then we'll consider these questions once we have those numbers. So let's make an A and a B for each of them. So A is going to be this one here. B will consider that one. Okay, so we have to find our moment of inertia. So we have our equations listed here. I stands for moment of inertia, and we're going to be going with this one, okay, because we can generalize it to be a rod, and we are rotating it through the center. That's going to be our equation that we're using for A. That's going to be our equation that we're using for B. Okay, so now the difference between A and B here, you're not just going to be able to use that equation one time. For this one, we can, because remember, this is our point of rotation, so we don't even have to think about that. We have the main mass that is out there. Okay, now for this one, we have to consider that mass and that mass because they're both rotating around that central axis. Okay, so for A, we're actually going to have to do 2 times this. Okay, so it'll be, I'll just do it twice. So let's say the moment of inertia for mass 1 plus moment of inertia for mass 2. That's kind of what it would look like if I generalized it. So it's going to be 1/12 times mass, which is 0.3 kilograms, times my length squared. Okay, so I'm going to do 2 of those. So take it times 2 because everything's going to be the same. The radius and weight does not change here to here. Alright, so for my second one here, I'll get the number up there in a minute. I have moment of inertia for the other one. I'm just going to have to find the moment of inertia of that one that's spinning out there. So you can see 1/3 is quite a bit larger than 1/12. So that's going to affect it quite a bit because the mass is all the way on the end. So our mass is 0.3 kilograms. And then our radius is now, or our length is 0.66 meters squared. Okay, so let's get you some numbers here. So I would put this in my calculator exactly as I have it if I want to do it all at once. And so 1/12 times 0.3 times 0.33 squared. And I am taking that times 2. So for the top one, I have a moment of inertia of 0.005. And do you remember what the units are? So it is a mass times a radius. So it's kilograms meters squared. So let's do this one now. So we have 1/3 times 0.3 times 0.66 squared. So for this one, we get 0.04356, so 0.044, and up here I probably could give us another number, it's 0.0054, and kilograms times meters squared. Alright, so let's compare these two. Which one's bigger? Well, you're like, well, there's a 5 there and 4 there, but there's an extra 0 here. So this one's pretty tiny, 0.0054 kilogram meter squared. This one 0.044. This one is quite a bit larger than that one, which makes sense because it is easier to rotate this kind of, or a baton like this, or is it easier to rotate a baton like that where you grab it on end? This is the easier one, so it should have less a smaller moment of inertia, a smaller resistance to rotation. Okay, so let's consider another question down here. So if the baton in example problem 3 is rotated about a point 1/4 from the distance from one round object, how does the moment of inertia compare to the two examples above? So now let's kind of draw our baton here. It looks like a barbell or something. And we're going to rotate here, so 1/4 of the way. So let's use our length that we had up there, 0.66, and that'll kind of help us break this into pieces. So 0.66 times 1/4, right? So I'll write that down. So 0.66 meters times 1/4, which is 0.25, and that's going to tell us that we have 0.165 meters. So that is 165 meters, and we have to figure out what this one's going to be, so we take that away from 0.66. So 0.6 minus 0.165, and that's 0.495 meters. Okay, so that's a 6 there, if we can see it. Alright, so I didn't change my mass. Those are again 0.3 kilograms. So how are we going to find the moment of inertia if we're spinning it right there? We're trying to turn that right there. Do I have to do one moment, or do I have to do two moments? How am I going to do it? Well, how many masses are rotating about that axis? We have this mass rotating and that mass rotating, so there are two. So we're going to have to do it with both of those. Okay, so my moment of inertia, and we would go with this one, okay, because we're going to kind of generalize it. Let's say we're kind of in the middle here. We're going to use that one. This probably isn't the best way to do it. I'm assuming there's equations here to do that, but we're going to get kind of a number. And we could generalize it here without a number, I suppose. Is it going to be, if I compare that to these two, is it going to be the same as this one, or is it going to be the same as that one, or different, or how is it going to be different? Well, this one's probably the easiest. That's probably the hardest, so this one's going to be in between. If I went 1/4 of the way in, then it's probably going to be, since this one's about splitting it in half, it might be double that. Okay, so let's just see if we can, let's just kind of see if we can get a number out of this. We have that 0.495, we already did that. So let's do our moments of inertia twice. So we got the mass on, fix that I, mass on the left and the mass on the right. So we have 1/12. Mass is 0.3 and our radius squared 0.165, and then we're going to do the other one, and it's 0.495 squared, and I'm just going to throw this all on my calculator so I can get a number. So 1/12 times 0.3 times 0.165 squared plus 1/12 times 0.3 times 0.495 squared. And I get 0.0068. That's kilograms times meters squared. So we can kind of scroll back up, compare our numbers. Whoops. So that's a 0.0054. We got 0.0068. So yeah, it's not bad. It's a little bit more than that, but not near as much as that. So that makes sense because this is 1/4 of the way there. So I'm pretty close to the center of the baton. All right. So let's look at one more question below here, and then we're going to be on to Newton's law of angular movement. Okay. So we're going to rank these objects from least to greatest for their moments of inertia and about the indicated axis. So this would be down through there, that axis, that axis, that axis. Okay, all spheres have equal masses and all separations are the same. Assume that the rod's mass is negligible. So we don't care about that yellow rod in between there. which one is going to be the least? Okay, so least to greatest. Which one's going to have the smallest moment of inertia? Okay, well, these ones, I can probably pick these out pretty easy now compared to what we did up above, but now we have this one thrown in there. So to understand moments of inertia, remember we have, in general, the mass times the radius squared. So which one of these is going to have the least mass away from the least radius, or the smallest radius? Okay, well, it's actually A is going to be the smallest, because that's taking this like you grabbed it here and then you started spinning it like that. Okay, or the other way. Either way, it doesn't matter. But we just want to figure out how to which one's going to be the hardest to spin or rotate. So this one, I have this little tiny radius, technically, because all my mass would be out here and here. Right, so I have this little tiny radius, and there's really not that much mass out there, because the center of mass is going to be kind of right in the middle there, right where you're spinning it. So A is going to be the least. Okay, so then the next ones here, we can kind of pick these out. That one's going to be the next one. That one's going to be the next one. That one's going to be the greatest. Okay, so B would be the greatest because we have the most mass, or we have a huge radius for that mass in comparison to those. So it's A, D, C, B. That's how we rank those. Okay, so this one kind of threw you for a little bit there. All right, so moving on. Newton's second law for rotational motion. So it states that angular acceleration is directly proportional to the net torque and inversely proportional to the moment of inertia. So that's our I down there. So this is angular acceleration. Okay, which if we remember what that is, we can kind of write that equation off to the side. That's going to be final minus initial angular velocity over time. We might need to relate that to that. Okay, and then we have net torque divided by moment of inertia. This in general is the equation. We can rewrite it to make it sound better or look better if we want to. But net torque, or torque in general, is Fr sine theta. And then moment of inertia, depending on whatever the object is, that's mr squared. So these three equations are going to relate to this one. Okay, there could be a torque that's causing an angular acceleration, and we could find the moment of inertia if we wanted to, and we could go even further if we know the object, and we could find a mass or a radius. So this little tiny equation seems pretty simple, but it can blow up into something like this, where we have to include or we have to use those three other equations in order to find one of the pieces of that. Okay, it's kind of a cool little equation, but it's a pretty loaded equation, even though it seems fairly simple. Okay, so it's net torque divided by moment of inertia will give me an angular acceleration. All right, so that is Newton's second law for rotational motion. I would say these ones are probably going to be the ones that have the most involvement mathematically compared to what we've done so far. Okay, so here are some things to think about. So note that the direction of the torque is important. So if you have something, you got to think of our unit circle. We have a torque that's going down. That is going to be a negative, because thinking that would be dropping below my axis of rotation, or below the 0 degrees, I suppose. If we have a torque going that way, that's positive, because that's above the axis. This is below the axis, that's above the axis. Okay. It's a torque on an object and the angular velocity of the object are in the same direction, then the angular velocity increases. Well, that makes sense. If I'm pushing on something and it's already spinning, then it's going to go faster. Maybe think of that game that you played as a kid. Maybe you still do it. You have quarters where you take it and you spin it, and then somebody else around the table tries to spin it again, right? So I have a quarter, it's rotating, and then you flick it, and you're trying to keep it rotating or get it faster and faster and faster, right? So every time you flick it, you're adding more torque to it, and yeah, that's going to increase my angular velocity. Okay, so if the torque and the angular velocity are in different directions, the angular velocity decreases. Well, you can kind of go back to this example again. You might have 4 people that are going around trying to spin that quarter, and one of your buddies wants to be the bad guy in the situation. He's going to try to spin it the other way. Well, as soon as he does that, it's boom, quarter flat on the table because he went the wrong way, unless he has a serious torque on it. Okay. So let's check out how we would use Newton's second law of rotational motion. So torque, a solid steel wheel, is free to rotate about a motionless central axis. All right, so looking at the wheel here. All right, this problem is in your textbook as well if you wanted to double check it. But we need, let's draw a picture here quick. So we have our wheel, okay, and then you have a central axis that does not turn, so maybe that's on an axle or something like that. But this is our wheel. The wheel spins. If you have a mass of 15 kilograms, so the mass of the wheel, 15 kilograms, diameter of 0.44 meters. So we don't want diameters, we want radius or radii, so that's 0.22 meters if we cut this in half. Okay, and starts at rest. So we need, so angular, since it's a rotational system, our angular velocity from rest is 0, and that's radians. Let's get rid of that. Let's fix that a little bit. Okay, so 0 radians per second. Okay, and we want to increase the wheel's rotation to 8 revolutions per second. So our final angular velocity is going to be 8 revolutions per second. That's revs per second. And we don't ever want to really work with revolutions per second when we're dealing with angular velocity, because that will not agree very much with our Newton's law there. So we can fix that in a minute. And our time is 15 seconds. Okay, so A, what torque must be applied to the wheel? And then B, how much force should you exert on the strap? Okay, so let's see what we can do here. So let's write out Newton's second law of rotational motion that we just talked about. So net torque on top there, and moment of inertia on bottom there. So angular acceleration is equal to the net torque divided by the moment of inertia. Okay, and let's write out those equations. So torque is going to be force times a radius. Moment of inertia here, since we have, it's a wheel, it's a cylinder. Okay, so the picture in the textbook shows a solid cylinder. That is 1/2 mr squared. And then our angular acceleration, might need to move, let's get rid of this guy for now. So our angular acceleration, if you remember that one, that is equal to final minus initial angular velocity over time. So what can we solve over here? Well, we have a final, initial, and time right there. That can get us an angular acceleration. And we have a mass and a radius, which can get us our moment of inertia. And we don't have a force, which that's what we're looking for right there. So let's find this and plug it into Newton's second law of rotational motion, and that will help us find that force we're looking for. Okay, so let's do moment of inertia first. So 1/2, mass is 15 kilograms, and our radius is 0.22 meters squared. So put that in your calculator. So 0.5 times 15 times 0.22 squared, you end up with 0.363. So 0.363, and again the label is kilograms times meters squared. And so that's one thing we're going to use. And let's get our angular acceleration here. So we're going to do final, and again we had to change that, so let's do that here quick. So if we have 8 revolutions per second, and we want to convert, okay, so that's 8 revs in 1 second. We're going to do a little track here. So what's our conversion here for revolutions? We want to go from revolutions to radians. Well, 1 revolution is 2 pi radians. Okay, and that will get us to radians per second. So the revolutions will cancel out. So we just take 8 times 2 pi. That's usually the quick way to go from revolutions to radian. So let's write that. So final angular velocity is going to be 8 times 2 pi, which is 50.27. And that is in radians per second. That's what we want. Okay, now let's use our angular velocity. So we're going to do final, which is at 50.27, minus initial, which is 0. So we don't really need to write that. Divided by time, 15 seconds. And that gives us an angular acceleration of 3.35. So that equals 3.35, and that's radians per second squared. Okay, so that's the other piece we're looking for. So let's use those in our formula now. So moment of inertia, angular acceleration right there. So we have 3.35 radians per second squared is equal to my torque, I don't know. Okay, I'm making a curly torque for tau divided by moment of inertia, 0.363 kilograms times meter squared. And then how do we get that out the bottom? Just multiply by it. 0.363. 0.363. So that's gone, that's gone. We gotta multiply those two here. So 3.35 times 0.363, and we get a torque of 1.216, so 1.22, and that'll be Newton meters. And now we're trying to get the force out of this. Okay, so torque, again, torque equals force times radius. So we can plug that in for torque, 1.22 Newton meters. We don't know the force, and we know the radius. Let's check it. It was 0.22 meters, or radius 0.22 meters. Divide by that. And we get 5.53. So my force is equal to 5.53, and that would be in newtons. So that's how much force we would need to get it to go from 0 to 8 revolutions per second. Okay, so if we apply the torque by wrapping a strap around the outside of the wheel, how much force would we have to exert on the strap? So I kind of did A and B at the same time without kind of realizing it. It says what torque must be applied to the wheel. That's our 1.22 newtons, so that's the answer for A. Oops. And then this would be our answer for B. So we kind of did both of those at once. Okay, so hopefully that helps show you how Newton's second law of rotational motion works. We have another problem on the next slide, so let's check that out quick. Okay, so I did this previously. Let's get rid of all this. Okay, so the wheel in example problem 4 is accelerated from rest to 8 revolutions per second in 5 seconds. So the difference here is our time is equal to 5 seconds. Okay, and we're going from 0 to 8 revs per second. So let's backtrack here, see if we can use some of the stuff on the last slide. So we are not changing our radius or anything. So we got 0.363 kilograms times meter squared for a moment of inertia. Okay. And then our angular acceleration, that's going to change because we're not doing it in 15 seconds anymore. We're doing it in 5 seconds. Okay. But we're not changing the 0 and 8 revs per second. So that's going to be 50.27 again. it would be 50.27 divided by 5 rather than 15. So 50.27 divided by 5, that's going to change our angular acceleration. So that makes it 10.05. And that's radians per second. Okay, so now we should have everything. We might need that radius again, 0.22 meters, if we don't remember it. And our mass was 15 kilograms. I don't know if we need that right now. So we have this. So second law. And that is over moment of inertia. So acceleration is equal to net torque over moment of inertia. And we will be looking for the force again. So we can find our torque, use our radius, we'll get our force. So we got 10.05 radians per second squared. I forgot my little squared down there. That's equal to net torque over moment of inertia, which is 0.363 kilogram times meter squared. So again, just multiply that out. And we will get a torque of 3.65 Newton meters. Okay, so now we'll use that in our torque equation. So 3.65 Newton meters is equal to force times radius. So force we don't know times the radius. So we'll just divide by 0.22 meters. And we will get a force equal to 16.59 newtons. Okay, so we're going to have to apply a 16.59 Newton force in order to do that in 5 seconds. Okay, so if we think about this, our time here is 5 seconds. Before it was 15 seconds, and we had 5.5. So we're cutting our time down by 3, right? So we're doing 1/3 the time. So really, if we're cutting our time down by 3, then our force should have to be 3 times as much. Okay, so if we look here, we had 5.53, which that makes sense that we had around 16.59. So that'd be about 3 times as much force to get it to go that fast in 1/3 of the time. Okay, so that's how we use Newton's second law of rotational motion. Okay, so that again is our acceleration is equal to the net torque divided by moment of inertia. So this is a little equation, is quite useful. It does have a lot of pieces to it because that blows up into a bigger equation, that does, and that does as well. So this equation with 3 variables actually has 3 different equations in it. So pretty useful. So hopefully that makes sense. Okay, so I'm going to skip ahead to the assignment. I want you guys to go all the way through 35. You can play with that simulation if you haven't done so. If we're doing this in class or as a day where I'm gone and you have to complete this, so please complete that and turn it in. Otherwise, work on numbers 21 through 35. And then I'm going to back up in this video a couple slides and work through some problems that we had. Okay, so there's your assignment. Ask questions if you have it. If you want to follow along in the video a little bit longer, we'll back up to some of the problems here. Okay, so these were the ones that we assigned torque yesterday. So we're going to look at some of these. The harder ones. So this guy, mass 43, sits 1.8 from a pivot point. Steve, whose mass is 52. How far from the center of seesaw should Steve sit? That's just like the problems that we started with. Okay, so back up in the video. That one should be not too bad to take care of. Bicycle chain has a radius of 7.7 centimeters. If the chain exerts a 35 Newton force on the wheel in the clockwise direction, what torque is needed to keep the wheel from turning? So it's essentially what torque is that generating and what opposite torque would we want to do. That's my force, that's my radius. However, notice that's in centimeters, so we're going to have to change that to meters. So our radius for this problem is 0.077 meters. Force is 35.0 Newton meters. Okay, so the wheel is turning clockwise, right? So the wheel has a negative torque. So what's the positive torque that I would have to exert on the wheel to keep it from turning? All right, so that's 17. 18. Two stationary baskets of fruit hang from strings on pulleys in different diameters as shown. What's the mass of basket A? So what you're going to be doing is you're going to find the torque on this little guy. So the torque on that one is going to turn, that same force is going to be turning the big one. Okay, so let's try this. So torque of the small gear there, we have a 1.1 centimeter radius of 0.011 meters, and that is a mass of 0.23 kilograms. Oops, not 0.25, 0.23. And we have to take that times 9.8 meters per second squared due to gravity. Okay, so 0.011 times 0.23 times 9.8, which generates a torque of 0.025 Newton meters. And then we need to figure out that mass. So to do that, we have to kind of think about how this works. So the key thing here, it says they're stationary baskets. So that means this torque from this basket is going to balance out with that torque. It's not rotating. Nothing's rotating. So I have to find the little torque or the torque of that, set it equal to the torque of that. Okay, so we have 0.025 Newton meters caused by the small gear, and that's balancing out the torque on the big gear. So the force, I don't know. And then we have our radius. So again, it's 4.5 centimeters, which you have to change. It's 0.045 meters. So divide. And again, that's going to give us a force. Okay, that's not really what we're looking for in the end. We're looking for the mass of the basket. Okay, so 0.025 divided by 0.045, which gives us a force of 0.56 newtons. Right? So how do we go from force to mass? Well, we know that that right there is going to be mass times gravity. Okay, which we know gravity is 9.8 meters per second squared. So we're going to have to divide 0.56 by 9.8. And that gets us to a mass of 0.057 kilograms. Okay, so at first it may have looked like, well, 0.56, well, that's bigger than that basket, right? Well, the baskets are different. Okay, I really would need a smaller basket here because I have a larger radius. Okay, so that smaller basket is going to have a larger radius to generate more torque. So dividing by 9.8 gets me that actual mass in kilograms. Okay, so hopefully that makes sense on that one. Let's look at this one. So suppose the radius of the larger pulley in problem 18 was increased to 6 centimeters. What's the mass of basket A now? So we need to just change that, and then so it'd be, rather than 0.045, it would be 0.06. So for this one, 0.025 Newton meters equals 0.06 meters times that force, and it's the same process here. Okay, so next one, a bicyclist of mass 65 kilogram. This is a challenge question. Stands on the pedal of a bicycle. The crank, which is 0.17 meters long. I'm going to scroll down a little bit here. The crank, which is 1.7 meters long. That's right there. Makes a 45-degree angle with the vertical as shown. Okay. The crank attached to the chain wheel, which has a radius of 9.7 centimeters. Okay, so that's that radius. What force must the chain exert to keep the wheel from turning? Okay, well, let's turn this into a force here. So force equals mass times gravity and that gives us 65 times 9.8, which is 637 newtons. So we're going to find the force exerted on that pedal right there. So it's 45 degrees there. So that's the number that we're going to be using again, because remember, if we have our foot there, okay, pushing down on the pedal, that's going to be 45 degrees as well. So if we want to calculate the torque caused by the push, so that's 637 newtons times 0.170 meters, because that's how long that lever is, times sine 45 degrees. That'll give us the torque of that foot pushing down on the pedal. Okay, so 637 times 0.170 times sine 45, and we get a torque of 76.57 Newton meters. Okay, well, this torque says what force must a chain exert to keep the wheel from turning. So we want the wheel to be generating an opposite torque in order to balance those out. So just like that basket problem, we're going to have this torque, which is 76.57 Newton meters, equal the torque of that gear right there. So we got to make sure you're paying attention to that, 9.7 centimeters. So force, we don't know, and our radius is going to be 0.097 meters. Okay, there is no angle involved here because this is a gear. It's circular, so we don't have to worry about the angle. That's a lever, so we had to pay attention to the angle. Okay, so we just divide by 0.097, and that'll give us our force that we want. So 76.57, I have that in my calculator, divide by 0.097, and we get a force of 789.41. So that's how much force that chain is going to have to be resisting in order to balance out the guy's foot there. Okay, so that takes care of all the torque problems that we had. I will try to make a video in the future to cover some of the harder ones, because I know these ones 21 through 35, those ones might be a little bit more difficult, but you can use the problems from earlier should be similar to some of those, like that one and that one. Okay, so use the example problems in the video to help you out. So I hope this video helped you quite a bit. It's quite a long one, but there's a lot of information here. So let me know if you have any questions. Good luck.